Hello everyone, welcome back. Today we'll try to solve one very interesting game using the Java programming language. You would have heard of something called Brainvita or Peg Solitaire as a kid, which involves moving a lot of marbles around the board so that you're left only with one marble in the middle of the particular board. Let's try to solve this problem using recursion. This will be a very interesting problem to solve, and let's try to do that. Let's get started. So initially let us create a class called Peg Solitaire. And then let's try to understand how we would want the structure of this particular class to be. So what we'll need is, we'll need some kind of a placeholder to hold the entire grid or the holes that we need. If you think about it, it's a two-dimensional array. So how it will look is something like this. We will want to think about it as a 7 cross 7 two-dimensional matrix, right? Now, it is not strictly a two-dimensional matrix when you actually want to play it, because a few of those areas in the four quadrants in the corners are not actually filled with any marbles, or there are no holes for you to fill it. So let us just consider them to be empty. Just call them -1 for now. So you'll have -1, then you'll have one peg here, then you'll have a peg here, then you'll have a peg here, then again you'll have nothing. Similarly, so if you look at it, this is the board that you're looking at. You'll have, wherever you have ones, they're all filled with marbles, and where there's a 0, it's going to be a hole which you have to fill. The rules of the game is very simple. You move one marble from across a particular marble into a hole, and then whatever marble you jump has to be removed from the board. So that's the simple rule of the game. So which means that in this case, if I were to remove this particular one and move it from here to the 0 here, the 1 in this place will get removed. And that's the way you keep creating more and more holes, and then you keep on jumping the marbles from one to another, so that you're left with only one marble in the middle of the middle of the board. So this is the rules of the game. Now if you look at it, this is a classic case of a recursive algorithm, wherein you keep trying. At every stage you have multiple options for you to move, and you select the best options and then try to arrive at the final solution. Now how you arrive at the best option is based upon the classic backtracking algorithm, wherein you recursively try each and every move and see if it is going to lead to a solution. If it leads to a solution, you end, and then you have the solution to be presented. But if you're not able to get a solution, you backtrack one level up and then try to find the other moves that will help you to reach the solution. You keep doing this again and again and again till you find a set of moves which is going to finally lead you to the solution that you want, which is having that one marble in the middle of the entire. So we have created a class called Peg Solitaire. The first thing that we will need is the board itself, right? So let's create the board. And now we just said that the board is going to be an array of arrays, right? It's going to be a 7 cross 7 array, two-dimensional array. For simplicity and for ease of development, let's keep this as an array list, right? Array list. Now it's an array list of array lists, right? So we'll have to parameterize it as well. And since I'm going to be storing the marbles as well as the holes as ones and zeros, and the non-playing areas as -1s, it's all going to be integers. So let me just keep them as integers. It's going to be called, let me call it grid. We need to have a list of all moves so that we present it in the end saying that this is the solution. So again, we'll have it as an array list. Array list of, for now we'll just call it empty. Let us keep this array list. Moves list. Alright. I'm just keeping them all as public as of now. I'm not going to make them private so that we don't waste time in creating getters and sets. Now every move, like we saw, comprises of a marble being moved from one location, jumping over one marble and moving to a blank space. So you have a from location, you have a to location, and you have a new hole that is getting created in between, which is a whole location. Now let's try to make this as into a data structure, right? In Java, we do not have a struct, so we'll just create another class here. Class move, right? And Let's create a move. So it has a location, which is nothing but an index. It's an integer. We'll call it from. Then we have integer. We have the whole. Then we have an integer, which is the to location. That's it, right? Now we'll just make it easier for us to instantiate this particular structure by creating a constructor for it. Move int from int whole int to. I mean, this is all boilerplate code. Anyway, we'll have to do this. Let's make it easier for us to print it in case we want to print a move. So how would you want to print it? So let's just override the toString method here. Public void toString. Sorry, it cannot be void. It has to be string. toString. And what we'll return is something like this. So we'll be returning it in the form of a parenthesis. We'll add the from, add a comma, the whole location, comma, and then the to location, and close it. Right? So the move object structure is ready for us. So now all of these moves are going to be stored in this moves list. Let me parameterize this. It's called move. It's an array list of all moves. So what we are going to do is we are going to see which of the grids are actually going to have a positive outcome, and we are going to separate them out from those which are not going to give a positive outcome. Now this leads us to a new kind of programming called dynamic programming and a concept of called memoization. What it basically means is if you're going to have a long program, a complex program, which is going to be solving the same problem again and again as part of its subproblems, so it makes sense for you to store some of the outcomes in some location, memory location. Usually it's a list. In this case, an array list or vector or wherever it is. And then you go and do a lookup. If you feel that a problem has already been solved and you just don't want to solve it again because it's going to take a longer time for you to solve it, you just go and refer to this list and see what the outcome is and then use that outcome as it is. That's called dynamic programming. It's a very great way to reduce the runtimes of long running programs. So let's create one more array list, and this time it's going to contain the entire grid itself. So it's going to be an array list of integers. This is how it's going to look like. Let's call this unsuccessful grid. Right? Great. Now, why have we created an array list of array list? Because it's finally going to contain this grid. A list of all grids like this. Right? So which is what it is going to keep inside here. Right? Now let's quickly write one constructor for the Peg Solitaire class. So Peg Solitaire. By default, you'll anyway have to give a grid as an input. So let's say array list of integer grid. Right? So we'll say this dot grid equal to grid. Creating some helper functions first so that it makes it easy for us to move forward. What we want to do is we will write a method to print the entire output when it comes out, which is nothing but moves list. So let's call that method print output. Public. No, let's keep it private. Private void print output. And what we need to do is for every move that is there in moves list, you go and print it. Move. Of course, a move cannot be printed as it is, so you just say we already created this toString here, so it's going to print this entire string as it is, right? Brilliant. So you've done that. Now let's try to go and print the entire grid itself, the board itself. So we'll say private void display grid. So we have a method to display the entire grid as well. You have to make a move. What do you have to do? Means the from location was 1 earlier and now becomes 0. Your to location now was 0 earlier, now becomes 1, and your whole, which is having 1 earlier, now becomes 0. Right? And let's try to write that. Let's make it private void make move, and we give the move as an input. So what we do is we say grid dot get move dot from. Let's try to understand how each one of these locations is actually represented on the board. So it's called 0, 1, 2, 3, 4, 5, 6. Then the next row will be 7, 8, 9, 10, 11, 12, 13. The next one will be 14, 15, 16, 17, 18, 19, 20, and so on. So this is the way we are going to be representing the entire grid. So which means if I want to reference this particular location, this is in row number 2, column number 1, 2, 3, 4. Now if you look at 10, if you divide this 10 by 7, what you get as a recursion is 1, which is nothing but the row number. And when you take the remainder, when you divide this by 7, whatever you get is the column number. So if you divide this by 7 and look at the remainder, it's 3. So you have 0, 1, 2, 3, which is the column in which this particular number is located. So we'll be using a similar method to resolve this particular move and actually make the move. So when we say that a move is going to have from location, to location, and whole location, what we are going to do is we are going to take the from location divided by 7, right? And then for us to set a value in a particular column, we need to do a set, and then this time we need to get the column value. We just saw that to get the row we need to divide it, and the quotient gives you the row number, and for you to get the column you need to get the remainder. So we'll get move dot from %7. Now this will give you the column, and here I'm going to be setting it as 0, right? Because we are making a move, because the from location is now going to be empty. Similarly, the whole location is again going to be held empty. Since we have something called a moves list, now let's add this to the moves list. Moves list dot add and close it. Now when we make a move, we also have to undo it, because it's a backtracking algorithm. So we keep making moves and then removing moves to see if it is going to be leading to a successful output or not. So in case we need to undo something, we need to do the exact opposite of what we did in move. So what we'll do is we'll just copy this entire thing as it is. We'll call this undo move, same move. So we'll say grid.get, instead of 0 it will become 1, instead of whole becoming 0 it will again become 1, and your 2 has become 0. It's just replacing everything. What we need to do is we need to pop the last value out, right? So what we'll be doing is remove, and I want to remove the object which is in the last index that is there. So what I'll do is moves list dot size minus. So I'm going to remove the last value that got added, right? Is equal to a pop that we are going to be doing. Great. Now let's move on to the next function which we'll be writing is, for any state of the grid, what are the different possibilities or the moves that are available for the player to play? Now let's compute that. Now this is going to be the heart of the algorithm here, right? Now let's look at it. So private, now for now we'll just keep it as void. We'll come back to what it should be returning. Compute possibilities, right? What I want to be returning is, I need it to return a list of all moves that can be used by the player. So it has to be an array list of move right? Possibilities equal to new array list, right? Since I'm going to be returning this possibilities back, let me replace this void with array list. Now what do we need to do? Let us go one by one. Now let us try to understand this algorithm. What we want to see is, for every hole that is there, which means for every zero that we encounter, we need to see if there are marbles which are two steps ahead of it in either direction, either above it, to its left hand side, to its right hand side, or below it. And if it is available, we need to see if there is a marble available one step before, to its left, to its right, to its top, to its bottom. If any of these is available, then there is a move possible, which means I can move a marble, jump over another marble and come into this hole, and I'll have to make use of this possibility. Now how do we code that, right? Now let's first go to the iteration part of it, where we'll be iterating through the entire array to check whether there is a zero available anywhere. So for int I equal to 0, I less than size plus for int j equal to 0, j less than grid dot, we are looking into the array list within the array list, get I dot size j plus plus. Now that's where we need to do a check. If the grid value is 0, how do you check that? Grid dot get I dot get j. Is it 0? If it is 0, then we need to check whatever we just discussed. We need to check if you have a marble two steps ahead of it. If there is a marble which is one step ahead of it in either direction, in all four directions, and if it is so, use it. Now what we'll do is we'll just make a quick check. What if we are on the top, you're on the sides of the board where there are minus ones on either side, right? So we need to do the corner case check as well. So we'll do a check saying if I minus 2 is greater than or equal to 0, which means it's not minus 1, then it makes sense for us to do our algorithm, right? Then what we'll do is we'll do our check. Why are we checking I minus 2 and not I minus 1? If I minus 2 is definitely not 0, is greater than 0, it means I minus 1 definitely will not be minus 1, right? So that way you don't have to do all the both the checks, one check should be enough. Now let us get this check saying, if the grid at location I minus 2, that is I minus 2th row, second row, and the j column, if that is equal to 1, and let's put this within a bracket, parenthesis, grid at I minus first location, row, I minus first row, in the same jth column is also 1, then our condition is satisfied. Then what we need to do is, we need to add this as a move to the list of possibilities that we have. So we say possibilities dot add. What do we have to add? It's a move. New move. We need to send the from. Now since we are creating the from as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 till 49. So sorry, till 48. It's a 7 cross 7 matrix, right? So we need to convert it into the locational number. In this case, we need to do I minus 2 into 7. I minus 2 multiplied by 7, just to make sure that the board mass is taken care of. comma, the whole location will be at I minus 1 into 7, correct? So I minus 1 into 7, and oops, we forgot to add factor the column as well. We need to add the j as well, plus j, and I into 7 plus j. Let's see if the parentheses are all okay. Yeah, they're okay. So what have we done here? We just converted the I and j coordinates of every from whole as well as the two locations into its respective location number by multiplying it by 7, which is multiplying the row by 7 and adding the column throughout. So this is how we are creating it, and that's how a move is being created. Great. Now let's look at the next opportunity. Now we just checked that I minus 2 greater than 0. Now let's look at j minus 2 less than 0, which means that we are on the bottom. We just try to see whether the row is getting satisfied. We are also now looking at the opposite direction, the y-axis, and seeing if we have an opportunity there as well. If j minus 2 is greater than or equal to 0, same principle. If j minus 2 is greater than or equal to 0, then j minus 1 will also be a valid value, valid location. Now the same thing has to be done here, where we are going to check if, just put the placeholders beforehand itself, if grid dot get at location I dot get at location j minus 2 is 1, and grid dot get at same location I get j minus 1, if both these conditions are satisfied, then we again have a new possibility or a new move. Possibilities dot add new move, same principle, I into 7 plus j minus 2. This time we don't need the parenthesis because its board mass is already taken care of. Come on, I into 7 plus j minus 1, I into 7 plus j. Let's see. Perfect. Now we are seeing the top as well as the bottom. Now let's look at the other extremes, wherein now we checked whether the I minus 2 was greater than 0, which means that I minus 2 is the beginning of a particular row. We need to look at the end of the particular row. One we need to check is if I plus 2, right, is less than 6, because we have only 7 rows and 7 columns. We need to check this. Sorry, it should be less than or equal to 6. It should be less than 7 or less than or equal to 6. If I plus 2 is less than or equal to 6, then let's do our checks. If grid dot get I plus 2 dot get j 1, I plus 1 j, condition is met. Possibilities dot add new move, same principle, I plus 2 into 7 plus j, comma, I plus 1 into 7 plus j, I into 7 plus j. Let's do the same thing for the y-axis. If j plus 2 is less than or equal to 6, same principle. If grid dot get I comma sorry I dot get j plus 2 is 1 grid comma I into 7 plus j plus 1 I into 7 plus j. Great. Now finally, after all of this, what we need to do is we need to return the outcome. Return possibilities. So what have we done? So we have created one array list which has all the possible moves that can be made for a particular configuration of the grid. It can be in any stage. It goes and computes all the possibilities. You can have 4 moves possible, 3 moves possible, 10 moves possible, and so on. But it just goes and checks all the boundary conditions and finds out all the universe of moves that you can actually make and gives it to you. Gives it to the program, to the solver. And the solver takes each move one by one and then tries to see if that move is going to lead to a final solution of one marble at the middle of the board. Right? Now we have all the helper methods ready. Now let's get to the main solve. Before that, let's have one more helper function which will also be about knowing when to stop the program, right? So we need to know whether we have just one marble left. So let's create something called get count. So private void, no, it will be an integer, int get count. So basically we're just going to get a count of all the marbles that are there, which are a count of all the ones which are there on the board. Now let's get into the solve. Public, public boolean solve. We'll keep it as boolean because we'll want to return a true or false at the end of each iteration that we are going to be taking recursively. Now how do we start it? Now what is the criteria for us? We had already created a grid. We are going to be taking one move at a time. We are going to be computing all the moves. Then you're going to take one move at a time, make the move, and then try to see if it is going to result in a grid which is going to finally end up in a final solution. So we will be doing this recursively, right? So after every move, we take the grid and then we pass on to solve again and again and again and again and again till we have a situation where either it has resulted in an unsuccessful grid, or we already have a grid which is already maintained in the unsuccessful grids, and we just look it up and then say, hey, you're not going to move anything anywhere further, so let us just stop here and then save the computing cycles and move on to the next option that we have. So what we'll do is we'll just check if the grid we actually have is available in the unsuccessful grid. So what you'll say is if unsuccessful grid contains our grid, right, then don't go further, just return false, right? You don't have to waste memory cycles, CPU cycles just for this. So instead what we'll be doing is, so this is the first condition. Next, let us check what is the exit condition when we actually have a case where the problem is solved. If get count is 1, then we are done. Then what shall we do? We'll display the grid, then we'll display the print the output, and then we'll say return true. So we are done. However, if we are still not reached the 1 mark that we wanted, we'll do our computation. So what we'll do is first let us compute the list of all possibilities which we just did just now. Moves compute possibilities. So now we saw that compute possibilities is going to go through this entire list of all checks and see whether there's a marble in these locations, and if there's a hole in another location, and then it computes all the possibilities for you for this particular grid state and gives it to you. Now here we are going to do one very tricky magical thing. What we are going to do is, to make the algorithm converge faster, we are going to sort this algorithm. We are going to sort the list of all moves, and for that we are going to make a few small changes to the classes. I'll tell you why you're going to sort this in a few minutes. Before that, what I want to do is, I want this moves is an array list, and I want to sort this array list. In Java, we have something called a comparable and a comparator interface, which helps you to create the logic through which you would want to compare two elements and then sort them in case you want to use any sort algorithm. So what we are going to do is, we are going to go back to our move class that we created, and instead of just calling it move, I'm going to make it implement the comparable interface. Right? Now by doing this, what happens is, I need to go and implement the method, which is nothing but the compare to method. So we are going to do it in ascending order. So what you're going to do is, we are going to see if the from location of each move is less than the from location of the other move, and whichever is smaller is going to be brought in first, which is nothing but the ascending order. So we are going to say return integer dot value of this dot from. I'm going to compare it to integer dot value of m dot from. M is what I'm comparing it with. So if these two are automatically compared, because these two are integers and they already have the compare to, they already implement the comparable interface, so you already have the way in which they'll be giving the results. So the two integers will be compared, and whichever is the smaller one will be given the higher priority, and it will be moved up in the list. So that way we are doing it in ascending order. So we have done given the algorithm what the methodology is to compare two moves. So we'll just go back to our solve method and say collections dot sort moves. Now it's automatically getting sorted in ascending order. Now, why are we sorting this? We see that the algorithm performs much better when we actually try to do it row by row, which means that you keep moving the barbells from the top and go to the bottom. The algorithm converges much faster, and this is one of the tricks that you would want to use to implement this. You can always choose not to use a sort, but the thing is, the compute time becomes extremely long. It might even go into some few. Now that we have all the moves ready, let's make a move. For moves grid, make move of this move. Right? Now after you make a move, just check once. Now the grid has changed, right? The zeros has become ones and ones have become zeros. So now you need to solve it again. So here is where we'll call the recursive algorithm again. Let's go recursive function again. If you solve this new state again, and if it is getting solved, then return true. Else, what do you have to do? You made a move, so you have to undo it. Undo the move, and that's it. This is the length of your entire algorithm. It's all being done by the recursive call to solve here. Now finally, you tried all the moves that you have, you've not found anything. So which means it's an unsuccessful grid configuration. So what you do is, you just add it to that list so that you can use it for your dynamic programming. If your unsuccessful grid does not contain, we'll put a not operator here, does not contain the current grid, unsuccessful grid dot add the grid. Now here is where we need to make another helper function. Now this is going to be slightly tricky. So what we need to do is, now grid is referring to, it's a reference to a particular object, array list of array lists. But then if you're going to add the same grid into your unsuccessful grid, now what will happen is every time you make changes to the grid, the unsuccessful grid is going to keep getting modified, which means that you're not actually having a unique version of a particular grid there. So you need to do a deep copy so that the reference doesn't get stored. A new value of grid itself is getting stored there. New instance of grid itself is getting stored there. So for that, let us create one small helper function for ourselves, and we'll call it deep copy. You can always use a clone operation as well, but then you do the same thing when you override the clone method. You need to go and give it the method in which you will be copying deeply from one object to another. So instead of that, we'll just use a private function, array list integer deep copy, and you're going to be passing an input array list. Let's call it input. So this is what is going. So this way we are going to be copying this deep from one item to another. So let's use that here. Instead of saying grid, I'll say deep copy of grid, and I'll be sending it out. And of course, if it doesn't return anything, then we return false. So great, we have solved this. Now let's try to see how to write the main function and call this public static void main. I'm just copying this from what I already have. So what you're going to do is we're going to create an array list of integers grid, and then you're going to instantiate this entire list of the grid items here. So this is exactly what we saw in the beginning. It's all going to be integers, and then finally we're going to add all of these into new Peg Solitaire and ask it to solve what we just asked it to do. Great, let's first see and compile and see whether this is working or not. Java C, Peg Solitaire to Java. Great. Now let's see. Java Peg Solitaire. It will take some time to try and solve it. What it is basically doing is it's making a move. It's looking at all the possible moves. It's making one move, and then because the grid has now changed, it is going and trying to recursively see how the new grid has come out. It solved it. Now let's see how the output is looking. Wow, it has reached the stage where there is only one marble which is created, but it's not in the middle, right? So if you look at the condition for solve, and it has given us the list of all the steps that you need to take to make this work. Now the one condition which we had given was it should be 1. Our final number of marbles in the board should be 1. Now let us make it slightly more specific. We'll tell it that the marble has to be only in the middle location and not anywhere else, right? Let's make a small change to our solve logic. Instead of saying just get count equal to 1, let's add and grid dot get at 3 equal to 1. Meaning we are saying that it should be specifically only in the middle and not anywhere else. Now let's again compile it. And let's run it again. It's running. This time we are given it an extra check for the final solve condition. Yes, it's returned. Let's see how it has solved it. Great. It's finally solved it so that we have only one marble in the middle, right? And if you just follow all of these steps one by one and see in any board, you'll be able to figure out that it will result in this solution for you, right? So to summarize, what we have seen is, we have taken the concept of recursion to solve another problem here. So in this case, Peg Solitaire, or Brainvita as we call it, is a board where we have marbles initially in the board with just one hole in the middle, and this is the classic pattern in which we play this game, and we keep making moves, each move being one marble jumping over another marble into a hole location, thereby creating two new holes. So the end result should be that only one marble should remain, and that one marble should be in the middle of that particular board. And to solve this, what we have done is we have recursively called a particular solve method, which is what we are seeing here. And this solve iteration, we check how many moves are possible. We make one move and again ask it to solve it. So by backtracking again and again, whenever we reach a stage where a grid is not resulting in a solution, we backtrack and try to see different moves which are available. And to make this much faster, we have used dynamic programming concepts and memoization concepts, wherein we are maintaining an unsuccessful grids list. And then every time we reach a stage where an unsuccessful grid has already been reached, we don't compute anything further, so that we save a lot of time as well as computing power and go to converge on the solution much faster. So hope this has been really helpful for you to further your understanding of how recursion can be used. This is a very fun way to understand this. It is not a very complicated program. Please do give it a try. In my next video, I'll be showing the same algorithm written in Python. Thank you very much for watching. Enjoy.